The fluorescent lights hummed overhead as Senior Airman Sarah Chen walked into the hangar at Langley Air Force Base, her steel-toed boots echoing against the concrete floor. It was 0500 hours, and most of the base was still asleep, but Sarah preferred these quiet moments before the chaos of the day began. She grabbed her coffee, black, no sugar, and headed toward the beast that had been haunting her dreams for the past 3 weeks. There it sat, like a wounded predator. An F-22 Raptor, the most advanced fighter jet in the world, worth $150 million of cutting-edge American aerospace engineering. To most people, it would look magnificent, even in its current state. But to Sarah, all she could see were the problems. The aircraft had been grounded for 21 days, and every single specialist who had touched it had walked away defeated. "Mornin', Chen." The voice belonged to Master Sergeant Rodriguez, her supervisor, a man who'd been working on aircraft since before Sarah was born. His weathered face carried the weight of decades spent elbow-deep in jet engines, and his skeptical expression had become as familiar to Sarah as her morning routine. "Mornin', Sergeant," she replied, not taking her eyes off the Raptor. Rodriguez approached, his clipboard already in hand. "Look, I know what you're thinking, but this bird has stumped everyone. We've had our best people on this. Thompson, Williams, even brought in Martinez from the depot. They all said the same thing. It's gonna need a complete engine replacement, maybe even structural work. We're talking about sending her back to Lockheed Martin." Sarah nodded, still studying the aircraft. She'd heard this speech before, not just about this particular F-22, but about dozens of impossible repairs throughout her 5-year career. The subtext was always the same. "You're good, Chen, but you're not that good. And besides, you're a woman in a field where women don't belong." Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The F-22 Raptor isn't just any fighter jet. It's a technological marvel that represents the pinnacle of American air superiority. With its twin Pratt & Whitney F-119 engines producing 35,000 pounds of thrust each, stealth capabilities that make it virtually invisible to radar, and the ability to cruise at supersonic speeds without using afterburners, the Raptor is quite literally irreplaceable. Only 195 of these aircraft were ever built, and production ended in 2011. When one goes down, it's not just expensive, it's a blow to national defense capability. Sarah had grown up in a small town in Ohio, the daughter of immigrants who had sacrificed everything for the American dream. Her father worked double shifts at a factory. Her mother cleaned offices at night. They didn't understand why their daughter wanted to work on airplanes instead of becoming a doctor or lawyer, but they supported her anyway. What they definitely didn't understand was why she wanted to join the military. "Sarah," her mother had said on the day she left for basic training, tears streaming down her face, "why do you want to go where they don't want you?" It was a fair question. The Air Force, like all branches of the military, had been slow to embrace women in technical roles. When Sarah arrived at her first duty station in 2019, she was often the only woman in the room, the only woman on the flight line, the only woman who raised her hand when they asked who wanted to work on the most challenging aircraft. But Sarah had something that couldn't be taught in any technical school, an intuitive understanding of how machines work. While other technicians followed diagnostic procedures step by step, Sarah could sense when something was wrong. She could hear it in the subtle change of an engine's rhythm, feel it in the vibration of a control surface, smell it in the hydraulic fluid that shouldn't be leaking. This gift, because that's what it was, a gift, had served her well throughout her career. She diagnosed problems that had stumped senior technicians, found solutions that weren't in any manual, and earned a reputation as someone who could fix the unfixable. But she'd also earned something else: resentment from colleagues who couldn't understand how a young woman could be better at their job than they were. The F-22 had been experiencing what the maintenance logs described as intermittent engine anomalies. That was military speak for, something's wrong but we don't know what. The symptoms were subtle. Slight variations in engine temperature, minor fluctuations in fuel flow, barely perceptible changes in thrust output. Any one of these issues alone would be within normal parameters. Together, they painted a picture of an aircraft that was slowly, mysteriously, falling apart. The first technician to work on the jet was Staff Sergeant Thompson, a 15-year veteran with an impeccable record. He'd run every diagnostic test in the book, replaced sensors, cleaned fuel lines, and checked engine mounts. The problems persisted. Next came Technical Sergeant Williams, who specialized in avionics systems. She suspected the flight computer was sending incorrect signals to the engines. After 3 days of testing and 2 software updates, the anomalies remained. Senior Master Sergeant Martinez was the final hope, a legend in the Air Force maintenance community, a man who'd worked on everything from F-16s to B-2 bombers. If anyone could solve this puzzle, it would be him. He spent a week methodically checking every system, every connection, every component that could possibly cause the issues they were seeing. On his final day with the aircraft, Martinez had called Rodriguez aside. "I hate to say this, Sergeant, but I think we're looking at catastrophic and Pearl engine damage, the kind of thing that doesn't show up on scans until it's too late. My recommendation is to ground this bird permanently and strip her for parts." That was 3 days ago. Now, as Sarah stood before the Raptor in the pre-dawn quiet of the hangar, she was the last hope for an aircraft that represented not just $150 million in taxpayer money. That was 3 days ago. Now, as Sarah stood before the Raptor in the pre-dawn quiet of the hangar, she was the last hope for an aircraft that represented not just $150 million in taxpayer money, but the culmination of decades of American aerospace innovation. Sarah's approach to aircraft maintenance was methodical, but not in the way they taught at technical school. While other mechanics started with the most likely causes and worked their way down a checklist, Sarah began with what she called listening to the airplane. She believed that every aircraft had its own personality, its own way of communicating what was wrong. She started her examination at 0530 hours, beginning not with diagnostic equipment or technical manuals, but with a simple walk-around inspection. Her trained eyes swept over every rivet, every panel, every surface of the Raptor's distinctive angular frame. The F-22's stealth coating required special attention. Any damage to the radar-absorbing material could compromise the aircraft's primary advantage. Still playing airplane whisperer, Chen? The voice belonged to Airman First Class Jackson, one of the younger mechanics who'd been assigned to assist her. His tone carried the particular brand of condescension that Sarah had learned to ignore over the years. "Something like that," she replied, running her hand along the leading edge of the wing. The Raptor skin was smooth, almost organic in the way it curved and flowed. Every angle had been calculated to scatter radar waves, every surface designed to make this deadly machine invisible to enemy detection. Sarah climbed up onto the maintenance platform that surrounded the aircraft's midsection. From here, she could access the engine intakes and begin her real investigation. The F-22's engines were masterpieces of engineering, each one capable of producing more thrust than 4 NASCAR engines combined, yet sophisticated enough to adjust their power output thousands of times per second. She opened the maintenance panel and connected her laptop to the aircraft's diagnostic system. Immediately, screens filled with data: engine temperatures, fuel flow rates, hydraulic pressures, electrical loads. To an untrained eye, it would look like gibberish. To Sarah, it was a language she'd been learning to speak fluently for 5 years. But the numbers weren't telling her the whole story. Every parameter was within acceptable limits. Every system appeared to be functioning normally. This was exactly what had frustrated the previous technicians. The aircraft looked perfect on paper, but clearly wasn't performing correctly in the air. Sarah's mentor, Master Sergeant Patricia Hawkins, had taught her something during her early days in the Air Force. The airplane never lies, Chen. If it's telling you something's wrong, something's wrong. The trick is learning to hear what it's really saying.
Hawkins had been one of the first women to work on fighter aircraft when the Air Force opened combat rules to women in the 1990s. She'd faced challenges that made Sarah's experiences look trivial. Death threats, sabotage, colleagues who would literally walk away rather than work with her. But she'd persevered and eventually earned the respect of even her harshest critics through sheer competence and an unshakable determination to do her job better than anyone else. The hardest part, Hawkins had called Sarah during one of their late-night conversations in the break room, isn't proving you're as good as the men, it's proving you're better. Because if you're just as good, they'll find an excuse to get rid of you. You have to be undeniably, unquestionably better. Sarah carried that lesson with her as she dove deeper into the F-22 systems. She pulled up the aircraft's flight history, studying the pilot reports from the last 6 months. The anomalies had started small, tiny variations that could be attributed to normal wear, atmospheric conditions, or even pilot technique. But over time, they'd grown more pronounced. The pattern was subtle, but it was there. Sarah noticed that the problem seemed to occur more frequently during certain types of maneuvers, specifically high G turns at altitude. The F-22 was designed to handle up to 9 Gs of acceleration, forces that would render most humans unconscious. But something about these extreme maneuvers was causing the mysterious engine issues. She cross-referenced the flight data with maintenance records, looking for any correlation between specific flights and the anomalies. What she found was interesting. The problems were most severe after training missions that involved air-to-air combat simulations, particularly those that required rapid altitude changes and aggressive maneuvering. Finding anything interesting? Rodriguez had appeared beside the maintenance platform, coffee in hand. Despite his earlier skepticism, Sarah could see genuine curiosity in his eyes. He'd been in maintenance long enough to recognize when someone was onto something. "Maybe," Sarah replied, not looking up from her laptop screen. "I want to check something." She pulled up the engine monitoring data from the aircraft's last flight, a training mission 2 weeks ago that had ended with the pilot reporting minor engine irregularities upon landing. The flight profile showed a typical air-to-air combat simulation: rapid climbs, sharp turns, aggressive dives, and sudden course corrections. But Sarah noticed something that the previous investigators had missed. During the most aggressive portions of the flight, there were microscopic variations in the synchronization between the two engines. The F-22's twin engines were designed to work in perfect harmony, their thrust outputs coordinated by sophisticated computer systems. But during high-stress maneuvers, that synchronization was slightly off. The difference was tiny. We're talking about variations measured in milliseconds and fractions of percentages. But in an aircraft as precisely engineered as the F-22, tiny differences could compound into major problems over time. "Jackson," Sarah called to her assistant, "I need you to pull the engine mount inspection records for the last 6 months." "The engine mounts?" Jackson looked confused. "Thompson already checked those. They're solid. Just pull the records." As Jackson reluctantly headed off to retrieve the maintenance files, Sarah continued her analysis. Engine mounts were critical components that secured the massive engines to the aircraft's frame. They had to be strong enough to handle the tremendous forces generated by the engines, yet flexible enough to absorb vibrations and allow for thermal expansion. If the engine mounts were degrading, it could explain the synchronization issues she was seeing, but the degradation would have to be so subtle that it wouldn't show up in standard inspections, the kind of problem that would take months to develop and would be nearly impossible to detect without knowing exactly what to look for. Sarah was beginning to form a theory, but she needed more data to prove it.
The maintenance records that Jackson brought back confirmed Sarah's suspicions. The F-22's engine mounts had been inspected multiple times over the past 6 months, and each inspection had found them to be within specifications. But Sarah noticed something that the previous investigators had overlooked. The mounts were at the very edge of acceptable tolerances, and they were degrading in a specific pattern. Aircraft engine mounts are subjected to incredible stresses. Every time a pilot pushes the throttles forward, the mounts must absorb and distribute forces that would tear apart a normal structure. Over time, these repeated stress cycles can cause microscopic changes in the metal. changes so small that they don't show up in standard inspections, but significant enough to affect the aircraft's performance. Sarah had seen this before, but in much older aircraft. The F-22 in front of her was relatively new, with only 1,200 flight hours on its airframe. Engine mount degradation typically didn't become an issue until after 3,000 hours or more. But this particular Raptor had been assigned to the Air Force's most aggressive training squadron, where pilots pushed both themselves and their aircraft to the absolute limits of performance. "I need to physically inspect the mounts," Sarah announced, causing Rodriguez to raise an eyebrow. "Chen, those mounts were just inspected last month. Martinez himself signed off on them." "I know, but I want to look at them with a specific focus on asymmetric stress patterns." Rodriguez set down his coffee and gave him his full attention. "Asymmetric stress patterns?" Sarah pointed to our laptop screen where she'd overlaid engine performance data with flight profile information. "Look at this. During aggressive maneuvers, especially left-hand turns at high G-loads, there's a measurable difference in how the engines respond. It's tiny, but it's consistent." "And you think that's caused by the engine mounts?" "I think one of the mounts is failing in a very specific way. It's still structurally sound. It'll pass every standard test we have. But under extreme loads, it's allowing just enough movement to throw off the engine synchronization." Rodriguez studied the data, his experienced eyes recognizing the pattern that Sarah was showing him. "Even if you're right, how do you prove it? We can't exactly stress test those mounts while they're installed." "Actually, we can." Sarah minimized the flight data and opened another program. "The Air Force just approved a new diagnostic protocol for detecting microscopic stress fractures in critical components. It uses ultrasonic resonance testing. Basically, we send sound waves through the metal and listen for irregularities in how they bounce back." The equipment Sarah needed wasn't standard maintenance gear. It was cutting-edge technology that had only been deployed to a few bases for testing. Fortunately, Langley was one of those bases, and the equipment was available in the Advanced Diagnostics Lab. Getting approval to use the new equipment required going up the chain of command. Rodriguez had to get permission from the maintenance officer, who had to get permission from the operations group commander, who had to justify the expense to the wing commander. In the military, even the simplest requests could become bureaucratic nightmares. But Sarah had something working in her favor: desperation. The F-22 had been grounded for 3 weeks, costing the Air Force thousands of dollars per day and lost training opportunities and degraded readiness. If there was even a chance that Sarah's theory could get the aircraft back in the air, it was worth pursuing. The approval came through at 1,400 hours. By 1,500 hours, Sarah was wheeling a cart full of specialized diagnostic equipment into the hangar, accompanied by Dr. Amanda Foster, a civilian engineer from the equipment manufacturer who would oversee the testing procedure. Dr. Foster was in her 50s, with graying hair and the confident demeanor of someone who'd spent decades solving complex technical problems. She'd worked on everything from space shuttle components to nuclear reactor systems, but this was her first time applying ultrasonic resonance testing to military aircraft. "So you think we're looking for stress fractures that are too small to see?" Dr. Foster asked as they set up the equipment. "Not exactly fractures," Sarah replied, carefully positioning sensors on the engine mount assemblies. "I think we're looking for changes in the metal's crystalline structure, microscopic deformations that are affecting the mount's flexibility under load." The testing process was painstakingly slow. Each engine mount had to be examined from multiple angles, with the ultrasonic sensors taking thousands of measurements per minute. The sound waves would penetrate the metal, bounce off internal structures, and return to the sensors, where sophisticated software would analyze the patterns for any irregularities. As the hours passed, a small crowd gathered around the F-22. Word had spread that the new diagnostic equipment was being used, and technicians from other squadrons had come to watch. I could feel their skeptical stares, could hear the whispered conversations about whether the girl mechanic was really onto something or just wasting everyone's time. At 5:30 p.m., Dr. Foster's equipment detected something unusual. The left rear engine mount showed subtle but consistent variations in its ultrasonic signature. Variations that suggested the metal had undergone stress-related changes at the microscopic level. "Interesting," Dr. Foster murmured, studying the readouts.
The mount is structurally intact, but there are definite signs of fatigue in the mounting bracket's stress distribution. Under normal loads, it would function perfectly, but under extreme loads, it would allow just enough movement to throw off the engine synchronization. Sarah finished. That's a very sophisticated diagnosis, Airman Chen. How did you know to look for this specific type of failure? Sarah was quiet for a moment, thinking about how to explain the intuitive process that had led her to this conclusion. I listened to what the airplane was telling me, and it was telling me that something was just slightly off. Not broken, but not quite right either. The crowd around the aircraft had grown larger, and I could see Rodriguez approaching with several officers I didn't recognize. The test results had attracted attention from higher up the chain of command. Colonel Matthews, the wing commander, was a pilot with over 3,000 hours in the F-22. He'd flown combat missions in Iraq and Afghanistan, and his opinion carried significant weight in the Air Force fighter community. Airman Chen, his voice carrying the authority of someone accustomed to being obeyed without question. I understand you may have found the source of our problem?
Sarah straightened her shoulders and looked Colonel Matthews directly in the eye. In the military hierarchy, a senior airman addressing a wing commander was like a freshman speaking to the university president. But Sarah had learned that competence earned respect regardless of rank. Sir, I believe we've identified microscopic stress-related deformation in the left rear engine mount assembly. The mount is structurally sound and passes all standard inspections, but under high G-load conditions, it's allowing enough flex to create synchronization issues between the engines. Colonel Matthews studied the diagnostic equipment, then looked at the data displayed on Dr. Foster's laptop. And this is causing the anomalies our pilots have been reporting? Yes, sir. The effect would be most noticeable during aggressive maneuvering, particularly during air-to-air combat training scenarios involving rapid direction changes and high G-loads. Dr. Foster stepped forward, adding her professional assessment. The ultrasonic resonance testing confirms Airman Chen's hypothesis. We're seeing clear evidence of microscopic structural changes that wouldn't be detected by visual inspection or standard testing protocols. Colonel Matthews was quiet for a long moment, processing the implications. If Sarah was correct, they'd found a type of failure mode that could affect other F-22s in the fleet, aircraft that had been subjected to similar high-stress training regimens. But if she was wrong, they were about to waste significant resources on an unproven theory. What's your recommended course of action, Airman Chen? Sarah had been preparing for this question. Sir, I recommend replacing the affected mount and conducting a fleet-wide inspection of high-time training aircraft using the ultrasonic testing protocol. If this type of degradation is affecting other Raptors, we need to identify and address it before it becomes a safety issue. The weight of her recommendation wasn't lost on anyone in the hangar. Fleet-wide inspections were expensive and time-consuming, but they were also necessary when a potential safety issue was identified. The F-22 was too valuable, both in terms of cost and strategic importance, to risk losing aircraft to preventable failures. How long to replace the mount? Colonel Matthews asked Rodriguez. If we order the part today, we could have it installed and tested within 72 hours, sir. Make it happen. The colonel turned back to Sarah. Airman Chen, you'll oversee the replacement and initial testing. If your theory is correct and this aircraft returns to full operational status, I want a detailed report on your diagnostic process. We may need to implement new inspection protocols across the fleet. As the officers walked away, Sarah felt a mixture of pride and pressure. She'd convinced the wing commander to act on her recommendation, but now she had to prove that her theory was correct. If the engine mount replacement didn't solve the problem, her credibility and possibly her career would be seriously damaged. The next 72 hours were among the most intense of Sarah's career. The replacement engine mount had to be special ordered from Pratt & Whitney, the manufacturer of the F-22's engines. While they waited for the part to arrive, Sarah worked with Dr. Foster to conduct ultrasonic testing on 3 other high-time F-22s at Langley.
The results were sobering. 2 of the 3 aircraft showed early signs of the same type of stress-related degradation that had affected the grounded Raptor. The problem wasn't isolated to a single aircraft. It was a fleet-wide issue that had gone undetected because existing inspection protocols weren't sophisticated enough to identify it. This is exactly the kind of problem the Air Force has been trying to prevent, Dr. Foster explained to Sarah as they reviewed the test results. Modern aircraft are so precisely engineered that tiny variations can have cascading effects throughout the entire system. What you've identified here is a classic example of how extreme operational conditions can cause unexpected failure modes. Sarah nodded, but her mind was focused on the practical implications. How many F-22 Raptors in the fleet have been subjected to high-stress training conditions similar to what we see here at Langley? Based on what I know about F-22 operations, probably about 60% of the active fleet. These aircraft are primarily used for air superiority training and homeland defense missions, both of which involve exactly the kind of aggressive maneuvering that causes this type of stress. The magnitude of the problem was becoming clear. If Sarah's theory was correct, dozens of F-22 Raptors could be operating with compromised engine mounts, potentially putting pilots at risk and degrading the Air Force's combat capability. On the second day of waiting for the replacement part, Sarah received an unexpected visitor. Master Sergeant Patricia Hawkins, her former mentor, had driven down from her new assignment at Dover Air Force Base specifically to see her. "I heard through the grapevine that you might have solved an impossible problem," she said, settling into a chair in the break room where they had so many conversations during Sarah's early career. "It's not solved yet," Sarah replied. "I won't know if I'm right until we install the new mount and test the aircraft. But you believe you're right." "I do." Hawkins smiled. "That's what separates good mechanics from great ones. The confidence to trust your instincts even when everyone else thinks you're wrong. Do you remember what I told you about having to be better than the men?" "You said I had to be undeniably, unquestionably better." "That's right. And you know what? You've achieved that. Word about this diagnosis has traveled all the way up to Air Force Material Command. They're calling it one of the most sophisticated failure analyses they've seen in years." Sarah felt a warmth spread through her chest. Hawkins had been more than a mentor. She'd been the example that proved it was possible for a woman to succeed in this field. Her approval meant more than any official recognition. "There's something else," Hawkins continued. "I've been asked to help develop new training protocols based on your diagnostic process. The Air Force wants to make sure that other technicians can learn to identify this type of problem before it becomes critical." The replacement engine mount arrived on the 3rd day, delivered by a special courier from Pratt & Whitney's facility in Connecticut. The part looked identical to the one it was replacing, a complex assembly of titanium and steel designed to withstand forces that would destroy most materials. Installing the new mount was a delicate process that required partially disassembling the aircraft's engine bay. Sarah worked alongside a team of experienced technicians, each movement carefully choreographed to avoid damaging the Raptor's sophisticated systems. As they worked, word of Sarah's diagnosis continued to spread throughout the Air Force maintenance community. Technicians from other bases called for details about the ultrasonic testing protocol. Engineers from aircraft manufacturers requested copies of her analysis. Even civilian aerospace companies expressed interest in her diagnostic methods. "You know," Rodriguez said during a brief break in the installation process, "I've been doing this job for 23 years, and I've never seen a single diagnosis generate this much attention." Sarah looked up from the engine mount assembly she was carefully positioning. "Is that good or bad?" "It's rare," Rodriguez replied. "Most maintenance work is routine, following established procedures to fix known problems. What you've done is identify a completely new failure mode and develop a method for detecting it. That's the kind of work that changes how the entire Air Force approaches aircraft maintenance."
The new engine mount was installed and torqued to specification by 1800 hours on the third day. Sarah spent the evening running diagnostic tests, verifying that all systems were functioning correctly and that the installation had been completed properly. Tomorrow would bring the real test, a functional check flight that would determine whether her theory was correct and whether the F-22 was ready to return to operational status.
The morning of the test flight dawned clear and cold, perfect conditions for evaluating the F-22's performance. Sarah arrived at the hangar at 0430, 3 hours before the scheduled flight, to conduct her pre-flight inspections. She'd barely slept the night before, her mind running through every possible scenario, every potential point of failure. Major Lisa Reynolds, the test pilot assigned to fly the mission, was already at the aircraft when Sarah arrived. Reynolds was one of the Air Force's most experienced F-22 pilots, with over 2,000 hours in the Raptor and a reputation for thorough, methodical test procedures. If anyone could detect whether the engine anomalies had been resolved, it would be her. "Morning, Airman Chen," Major Reynolds said, looking up from the flight plan she was reviewing. "I understand this bird has been giving everyone trouble." "Yes, ma'am. We believe we have identified and corrected the source of the engine synchronization issues. Walk me through what you found." Sarah spent the next 20 minutes explaining her diagnosis, the ultrasonic testing results, and the engine mount replacement. Major Reynolds listened intently, occasionally asking technical questions that demonstrated her deep understanding of the F-22 systems. "Microscopic stress deformation," Reynolds mused. "That's not something I would have thought to look for. How did you know to investigate the engine mounts?" The data showed that the problems were most severe during high-G maneuvers, particularly left-hand turns. That suggested something was causing asymmetric responses between the engines, and the engine mounts were the most likely culprit. "And you think the replacement mount will solve the problem?" "I believe so, ma'am. The new mount should provide consistent support for both engines, eliminating the synchronization issues." Major Reynolds nodded and returned to her pre-flight preparations. As a test pilot, she'd learned to trust the technicians who maintained her aircraft, but she also knew that ultimately, the proof would be in the flying. The test flight profile was designed to replicate the conditions that had consistently produced the engine anomalies. Reynolds would take the F-22 through a series of increasingly aggressive maneuvers, monitoring engine performance throughout the flight. If Sarah's repair had been successful, the engine should operate in perfect synchronization regardless of the aircraft's attitude or G loading. At 8040 hours, Major Reynolds fired up the F-22's engines for the first time since the mount replacement. Sarah stood on the flight line with Rodriguez and Dr. Foster, listening to the distinctive sound of the twin F-119 turbofans spinning up to idle power. To her trained ear, the engines already sounded different, more harmonious without the subtle discordance that had been present before. "Engine parameters look good," Reynolds reported over the radio, both engines showing normal temperatures and pressures. The F-22 taxied to the runway, its angular form casting sharp shadows in the morning sun. Even on the ground, the Raptor looked like it was moving fast. Its swept wings and twin tails suggested speed and agility, even at rest. "Langley Tower, Raptor 01 ready for departure." "Raptor 01, you're cleared for takeoff. Winds 270 at 8 knots. Major Reynolds advanced the throttles, and the F-22 began its takeoff roll. The twin engines produced a sound unlike anything else in aviation, not the raw roar of older fighters, but a more refined howl that spoke of sophisticated engineering and immense power held under precise control. The Raptor lifted off after just 800 feet of runway, its thrust-to-weight ratio allowing it to climb almost vertically if needed. But Reynolds kept the ascent shallow, allowing time to monitor engine performance as the aircraft gained altitude and speed. "Engine sync looks perfect," she reported over the radio, both engines showing normal temperatures and pressures. Sarah felt her shoulders relax slightly. The first phase of the test was going well, but the real challenge would come during the high-G maneuvering portion of the flight. At 20,000 feet, Major Reynolds began the tactical portion of the test. She put the F-22 through a series of combat maneuvers designed to stress both the engines and the airframe. Barrel rolls, split S maneuvers, high G turns, and rapid altitude changes. Each maneuver was performed with increasing intensity, pushing the aircraft closer to its operational limits. "Still showing perfect engine synchronization," Reynolds reported after completing a 7G turn that would have rendered most people unconscious. "No anomalies detected."
Back on the ground, Sarah monitored the telemetry data streaming back from the aircraft. Every parameter was within normal limits, every system functioning exactly as designed. The engine mount replacement appeared to have completely eliminated the problems that had grounded the Raptor for 3 weeks. But the most challenging part of the test was still to come. Reynolds had saved the most aggressive maneuvers for last, 9G turns in both directions, designed to recreate the exact conditions that had consistently produced engine anomalies in the past. Beginning maximum performance evaluation, Reynolds announced executing 9G left turn. Sarah held her breath as she watched the telemetry display. This was the maneuver that had reliably triggered engine synchronization problems before the repair. If her diagnosis had been correct, the engine should maintain perfect coordination throughout the turn. Wow, Reynolds' voice came over the radio, tinged with surprise. That was completely different. No vibration, no power variations, engine stayed perfectly synchronized throughout the entire maneuver. But test flight continued for another 30 minutes, with Reynolds putting the F-22 through every conceivable stress scenario. Each test produced the same result: perfect engine performance with no sign of the anomalies that had plagued the aircraft before Sarah's intervention. As the Raptor approached Langley for landing, Sarah allowed herself to feel a sense of accomplishment. She'd not only solved an impossible problem, but she'd developed a diagnostic technique that could prevent similar issues throughout the F-22 fleet. Langley Tower, Raptor 01 requesting straight-in approach to runway 25. Raptor 01, you're cleared to land runway 25. Welcome home. The F-22 touched down smoothly, its drag chute deploying to slow the aircraft on the long runway. As it taxied back to the hangar, Sarah could see that a small crowd had gathered to witness the conclusion of the test flight. Major Reynolds shut down the engines and opened the canopy, pulling off her helmet as ground crew positioned the maintenance ladder. Her first words as she climbed out of the cockpit were directed at Sarah. "Outstanding work, Airman Chen. That aircraft flies like it's brand new. Whatever you did, you fixed it completely."
The successful test flight marked a turning point, not just for the grounded F-22, but for Sarah's career and the Air Force's approach to advanced aircraft maintenance. Within hours of Major Reynolds' post-flight debrief, word of the successful repair had reached the highest levels of the Air Force hierarchy. Sarah was completing her post-flight inspections when Rodriguez approached with news that would change everything. "Chen, you need to come with me. The wing commander wants to see you, and he's not alone." In Colonel Matthews's office, Sarah found herself facing a room full of high-ranking officers she'd never seen before. There was a general she didn't recognize, several colonels with technical specialty badges, and a civilian in an expensive suit who introduced himself as a representative from Air Force Materiel Command. "Airman Chen," Colonel Matthews began, "your diagnostic work on this F-22 has attracted attention from the highest levels of the Air Force. General Morrison here is the Director of Aircraft Maintenance for Air Combat Command, and he's flown here specifically to discuss your findings." General Morrison was a tall, imposing man with silver hair and the confident bearing of someone who'd spent decades in positions of authority. But when he spoke to Sarah, his tone was respectful, almost deferential. "Airman Chen, I've been in aircraft maintenance for 30 years, and I've never seen a single diagnostic procedure generate this level of interest. Your identification of microscopic stress deformation as a failure mode has implications far beyond this single aircraft." Sarah straightened in her chair. "Sir, I believe this type of degradation could be affecting other high-time F-22s throughout the fleet." "That's exactly what we're concerned about," the general replied. "We've already ordered ultrasonic testing equipment to be deployed to every base that operates F-22s. If your theory is correct, we could be looking at a fleet-wide maintenance issue that's been undetected for years." The civilian from Air Force Materiel Command leaned forward. "Airman Chen, we'd like you to help develop a standardized testing protocol based on your diagnostic process. This could become a new requirement for all high-performance military aircraft." The magnitude of what they were proposing began to sink in. Sarah's discovery wasn't just solving a single aircraft's problems, it was potentially revolutionizing how the Air Force approached preventative maintenance on its most advanced fighters. "There's something else," General Morrison continued as the meeting concluded.
The Air Force Institute of Technology has expressed interest in your diagnostic methodology. They'd like you to consider attending their graduate program in aerospace engineering with a focus on developing advanced maintenance technologies. Sarah's mind raced. The Air Force Institute of Technology was the military's premier educational institution for technical training. A graduate degree from AFIT would open doors she'd never imagined possible. Sir, I'm honored by the offer, but I'm just a senior airman. I don't have the educational background for graduate-level coursework. Actually, you do, one of the colonels interjected. Your diagnostic work demonstrates a level of technical sophistication that most engineers with advanced degrees never achieve. The Institute is prepared to waive the normal prerequisites based on your demonstrated competence. Over the next hours, Sarah learned that her repair of the F-22 had set in motion a chain of events that would affect Air Force maintenance operations for years to come. New testing protocols would be developed and implemented across the fleet. Training programs would be created to teach other technicians her diagnostic methods. Research would be conducted to identify other potential failure modes that current inspection procedures might miss. There's something else, General Morrison said as the meeting concluded. The Air Force is nominating you for the John L. Levital Award, the highest honor given to enlisted personnel for outstanding technical achievement. Your work on this F-22 represents exactly the kind of innovation and excellence that award was created to recognize. As Sarah left the colonel's office, her head spinning from everything she'd learned, she found Rodriguez waiting in the hallway. His expression was a mixture of pride and amazement. 23 years I've been doing this job, he said, shaking his head. I've never seen anything like what just happened in there. You know what this means, don't you? Sarah wasn't sure she did. The events of the past few hours had moved so quickly that she hadn't had time to process their implications. It means you've just changed how the Air Force thinks about aircraft maintenance, Rodriguez continued. Every high-performance aircraft in the inventory is going to be inspected using methods you developed. Every maintenance technician in the service is going to learn diagnostic techniques based on your work. As they walked back towards the hangar, Sarah caught sight of the F-22 that had started it all. The Raptor sat in its parking spot looking no different than it had 3 weeks ago when it was grounded with mysterious engine problems. But now, it was fully operational, ready to resume its mission of defending American airspace. Rodriguez, Sarah said, stopping to look at the aircraft. Can I ask you something? Of course. 3 weeks ago, when I first said I wanted to investigate this problem, you didn't think I could solve it, did you? Rodriguez was quiet for a moment, considering his answer. Honestly, no, I didn't. Not because you weren't capable, but because Martinez, Thompson, and Williams had all failed. These are some of the best technicians in the Air Force with decades of experience between them. Then why did you let me try? Because, Rodriguez said, sometimes the fresh perspective is exactly what's needed, and because Patricia Hawkins called me before you were assigned to my shop. She told me you had something special, something that couldn't be taught in any technical school. She said you could listen to airplanes in a way that few people ever could. Sarah smiled, thinking about her mentor and the lessons she had learned over the years. What do you think will happen now? Now, you're going to become one of the most famous aircraft maintenance technicians in Air Force history. Your diagnostic methods are going to be studied and taught for decades, and every young woman who wants to work on aircraft is going to have you as an example of what's possible. The weight of that responsibility was both exciting and daunting. Sarah had never set out to become a symbol or a pioneer. She'd simply wanted to fix aircraft and do her job to the best of her ability. But she was beginning to understand that sometimes excellence in one area naturally leads to influence in others. There's something else, Rodriguez added with a grin. That F-22 you just fixed, the pilots have nicknamed it Sarah's Bird. From now on, every time it flies, it's going to carry your name with it. As they reached the hangar, Sarah took one last look at the F-22. In a few hours, it would be returned to operational status, ready to resume its role in protecting American airspace. Pilots would once again trust their lives to its sophisticated systems, confident that every component was functioning exactly as designed. But for Sarah, the aircraft represented something more than just a successful repair. It was proof that determination, intuition, and technical skill could overcome any challenge regardless of what others might think was possible. It was evidence that excellence knew no gender, no background, no preconceived limitations. Most importantly, it was a reminder that sometimes the most complex problems have solutions that are waiting to be discovered by someone willing to listen carefully and think differently.
6 months after the successful repair of the F-22, Sarah found herself standing in front of a classroom filled with aircraft maintenance technicians from around the world. The Air Force had invited representatives from allied nations to learn about her diagnostic methodology, and Sarah had been tasked with explaining her approach to an audience that included some of the most experienced aircraft mechanics in the international aerospace community. The key to advanced diagnostic work, Sarah explained, clicking to the next slide in her presentation, isn't just following established procedures. It's learning to recognize patterns that don't fit the expected parameters, even when those patterns are so subtle that they fall within normal operating ranges. In the audience, she could see faces representing a dozen different countries and air forces. There were grizzled master sergeants from the Royal Air Force, technical specialists from the German Luftwaffe, and maintenance officers from the Royal Australian Air Force. All of them had come to Langley to learn about the diagnostic techniques that had solved one of the most challenging maintenance puzzles in F-22 history. The past 6 months had been a whirlwind of activity for Sarah. The ultrasonic testing protocol she'd pioneered had been implemented across the entire F-22 fleet, revealing stress-related degradation in 37 aircraft, problems that would have eventually led to more serious failures if left undetected. Her work had potentially prevented multiple aircraft losses and saved the Air Force hundreds of millions of dollars. But the impact of her discovery extended far beyond the F-22 program. Other aircraft manufacturers had adopted similar testing protocols for their high-performance aircraft. The diagnostic methodology she'd developed was being applied to everything from commercial airliners to space launch vehicles. The ultrasonic resonance testing equipment allows us to detect changes in metal structure that are measured in nanometers, Sarah continued, gesturing to the sophisticated diagnostic equipment displayed at the front of the classroom. These changes are far too small to be detected by visual inspection or traditional testing methods, but they can have significant effects on aircraft performance. After her presentation, Sarah was approached by Dr. Elizabeth Hartmann, a materials scientist from the European Space Agency. Dr. Hartmann was particularly interested in applying Sarah's diagnostic techniques to spacecraft components, which were subjected to even more extreme stress conditions than fighter aircraft. Ms. Chen, your work represents a fundamental advancement in predictive maintenance technology. We believe your methods could help us prevent component failures in our spacecraft that could otherwise result in mission loss. Sarah had grown more comfortable with the attention her work had generated, but she still found it surreal to be discussing her diagnostic techniques with some of the world's leading aerospace engineers. A year ago, she'd just been another aircraft maintenance technician working night shifts in a base hangar. Now, she was being consulted by international space agencies and defense contractors. The formal recognition of Sarah's achievement had come in the form of the John L. Levitow Award, presented to her by the Chief of Staff of the Air Force in a ceremony at the Pentagon. The award recognized her exceptional technical achievement and innovation in aircraft maintenance that resulted in significant cost savings and improved fleet readiness. But for Sarah, the most meaningful recognition had come from her peers. Aircraft maintenance technicians from around the Air Force had reached out to share their own stories of challenging repairs and innovative solutions. She'd become a symbol of what was possible when technical expertise was combined with creative thinking and persistent determination. The Air Force Institute of Technology had also followed through on their offer, and Sarah was scheduled to begin graduate studies in aerospace engineering the following year. Her course of study would focus on developing advanced diagnostic technologies for next-generation aircraft, building on the foundation she had established with her F-22 work.
The future of aircraft maintenance, Sarah explained to the international audience, lies in predictive analytics and early detection of potential problems. By identifying issues before they become critical, we can maintain higher aircraft availability rates while reducing maintenance costs and improving safety. One of the questions from the audience came from a young female technician from the Canadian Air Force. Ms. Chen, as a woman working in aircraft maintenance, have you faced challenges related to acceptance in a male-dominated field? Sarah paused, considering how to answer the question honestly while remaining professional. There have been challenges, she admitted, but I've learned that competence and results speak louder than prejudice. When you consistently demonstrate that you can solve problems others can't, people stop focusing on your gender and start focusing on your capabilities. The Canadian technician nodded, clearly finding inspiration in Sarah's words. After the formal presentation ended, several female technicians from various air forces approached Sarah privately, seeking advice and encouragement for their own careers. The most important thing, Sarah told them, is to never let anyone else's limitations define what you think is possible. When people say, women don't fix jets, prove them wrong by fixing jets better than anyone else. That evening, Sarah received a call from Master Sergeant Patricia Hawkins, who had been following her former student's meteoric rise with pride and satisfaction. I saw the video of your presentation today. You have become everything I hoped you could be when I first met you 5 years ago. I couldn't have done any of this without your mentorship. You showed me that it was possible for a woman to succeed in this field. No, she corrected gently. I showed you it was possible. You proved it was inevitable. As Sarah reflected on the conversation later that night, she thought about the journey that had brought her to a small town in Ohio to international recognition as an aerospace maintenance expert. The path hadn't always been easy, but each challenge had taught her something valuable about perseverance, innovation, and the importance of believing in herself even when others didn't. The F-22 that had started it all, Sarah's bird, was still flying regular missions, its engines operating in perfect synchronization thanks to the engine mount replacement she had recommended. Every flight was a testament to the power of careful analysis, creative thinking, and the willingness to challenge conventional wisdom when the evidence suggested a different approach. The next generation of aircraft would be even more complex, with systems that push the boundaries of current technology. They would require maintenance technicians who could think beyond established procedures, who could recognize patterns that didn't fit conventional categories, and who could develop innovative solutions to problems that hadn't been encountered before.
Sarah was ready to help train those technicians, to share the lessons she'd learned, and to continue pushing the boundaries of what was possible in aerospace maintenance technology. 2 years had passed since Sarah's breakthrough diagnosis of the F-22 engine mount problem, and her influence on Air Force maintenance operations continued to expand. She was now a technical sergeant, having been promoted ahead of her peers in recognition of her exceptional contributions to aircraft readiness and safety. The ultrasonic diagnostic protocol she'd developed had been adopted not just by the Air Force, but by aircraft maintenance organizations around the world. Boeing had incorporated her testing methods into their maintenance recommendations for the 787 Dreamliner. Airbus was using similar techniques to monitor stress patterns in their A350 aircraft. Even NASA had adopted her diagnostic approach for monitoring structural integrity in their spacecraft. Sarah's current assignment was at the Air Force Test Center at Edwards Air Force Base in California, where she worked with the most advanced aircraft in the American inventory. Her role had evolved from hands-on maintenance to research and development, focusing on creating next-generation diagnostic technologies for aircraft that were still in the design phase. The future of aerospace maintenance, Sarah explained to a group of visiting aerospace industry executives, will be built around continuous monitoring and predictive analytics. Instead of waiting for problems to develop, we'll identify potential issues months or even years before they become critical.
The technology she was helping to develop incorporated artificial intelligence algorithms that could analyze thousands of data points in real time, identifying patterns that human technicians might miss. The system would continuously monitor aircraft performance, automatically flagging any deviations that suggested developing problems. Imagine, Sarah continued, an aircraft that can tell you exactly when a component will need replacement, not after it fails or shows obvious signs of wear, but months before it reaches its failure point. That's the direction we're heading. But Sarah's most significant current project was something that would have seemed like science fiction just a few years earlier, developing maintenance protocols for the Air Force's next-generation fighter aircraft, which incorporated technologies that pushed the boundaries of current engineering knowledge. The new aircraft, still classified and known only by its program designation, used materials and systems that required entirely new approaches to maintenance and diagnostics. Traditional inspection methods were inadequate for components made from advanced composites and metamaterials that behaved unlike anything previous aircraft had used. Working alongside a team of engineers and scientists, Sarah was helping to define how these revolutionary aircraft would be maintained throughout their operational lives. Her experience with the F-22 had taught her that even the most advanced aircraft could develop unexpected problems, and that the maintenance community needed to be prepared for failure modes that hadn't been anticipated during the design phase. The challenge, Sarah explained to Dr. Michael Foster, the program's chief engineer, is that we're dealing with materials and systems that don't have decades of operational history. We can't rely on experience to tell us what's likely to fail or how it's likely to fail. Dr. Foster nodded, understanding the implications. That's why we need diagnostic systems that can learn and adapt, systems that can identify problems we haven't thought of yet. Sarah's team was developing what they called intelligent maintenance systems, networks of sensors embedded throughout the aircraft that would continuously monitor everything from structural stress to electrical system performance. The data would be analyzed by machine learning algorithms trained to recognize patterns that indicated developing problems. The system was designed to go far beyond traditional maintenance approaches. Instead of following predetermined inspection schedules, maintenance would be performed based on the actual condition of each individual aircraft. A fighter that had experienced heavy use would receive more frequent attention, while aircraft with lighter usage could extend their inspection intervals. We're essentially creating aircraft that can diagnose their own problems, Sarah explained to a group of maintenance officers who would eventually oversee operations of the new fighters. The aircraft will tell us what needs attention, when it needs attention, and what specific procedures should be followed. The implications of this technology extended far beyond military aviation. Commercial airlines were already expressing interest in Sarah's diagnostic systems, seeing the potential for significant cost savings and improved safety. If aircraft could predict their own maintenance needs, airlines could optimize their schedules to minimize disruptions while ensuring that safety was never compromised. Sarah's work had attracted attention from unexpected quarters. The automotive industry was exploring how her diagnostic techniques could be applied to electric vehicles and autonomous cars. The shipping industry wanted to know if similar methods could monitor the structural integrity of large cargo vessels. Even the energy sector was interested in using her approach to monitor wind turbines and other critical infrastructure. But perhaps the most significant recognition of Sarah's achievements came when she was selected to attend the Air Force's prestigious Squadron Officers School, a leadership development program typically reserved for officers. As an enlisted technician, her selection was highly unusual and reflected the Air Force's recognition that her contributions extended far beyond traditional maintenance work. Technical Sergeant Chen, Colin Williams, the commandant of the school, explained during her orientation, "Your selection for this program reflects the Air Force's evolving understanding of leadership. Leadership isn't just about rank or position. It's about the ability to influence positive change and drive innovation." Sarah's presence in the program alongside Air Force officers was initially met with some skepticism from her classmates. But as they learned about her background and achievements, that skepticism quickly transformed into respect and admiration. "I've never met anyone who's had such a direct impact on how the Air Force operates," Captain Jennifer Martinez told her during a break between classes. "Your diagnostic work has literally changed how we think about aircraft maintenance." The leadership training Sarah received at Squadron Officer School prepared her for the next phase of her career, transitioning from technical expert to program manager. She was being groomed to oversee the implementation of advanced diagnostic systems across the entire Air Force fleet, a responsibility that would affect thousands of aircraft and tens of thousands of maintenance personnel. As Sarah reflected on her journey from small-town aircraft enthusiast to Air Force technical leader, she was struck by how much had changed, not just in her own career, but in the broader aerospace maintenance community. The field was becoming more sophisticated, more data-driven, and more reliant on advanced technology. But she also recognized that the fundamental principles that had guided her breakthrough work on the F-22 remained relevant. Careful observation, creative thinking, and the willingness to challenge conventional wisdom when the evidence suggested a different approach. The aircraft of the future would be more complex than anything currently flying, but they would also be smarter, more self-aware, and better able to communicate their maintenance needs to the technicians responsible for keeping them operational.
5 years after her initial diagnosis of the F-22 engine mount problem, Technical Sergeant Sarah Chen found herself standing before a congressional subcommittee explaining how her innovations had revolutionized military aircraft maintenance and saved the Department of Defense hundreds of millions of dollars. "Honorable members of the committee," Sarah began, addressing the panel of senators and representatives, "the diagnostic technologies we've developed have fundamentally changed how the military approaches aircraft readiness and maintenance planning." The hearing was part of a broader congressional review of defense spending and innovation. Sarah had been called to testify about the cost savings and operational improvements that had resulted from implementing her diagnostic protocols across the Air Force fleet. Technical Sergeant Chen asked Senator Patricia Williams, the committee chair, "Can you quantify the financial impact of your innovations on Air Force operations?" Sarah consulted her prepared notes. "Yes, ma'am. Over the past 5 years, the predictive maintenance protocols we've implemented have prevented an estimated 47 aircraft groundings that would have required major component replacements. The cost savings from early detection and preventive maintenance exceed $340 million. But the financial savings, significant as they were, represented only part of the story. Sarah's diagnostic methods had also improved aircraft availability rates across the fleet. Planes were spending more time in operational status and less time undergoing unexpected repairs. More importantly, Sarah continued, we've prevented potential safety incidents by identifying structural problems before they became critical. While it's impossible to quantify the value of preventing aircraft accidents, the safety improvements may be the most significant benefit of these programs. After her congressional testimony, Sarah was approached by representatives from several major aerospace companies. Boeing, Lockheed Martin, and Northrop Grumman were all interested in hiring her to lead their advanced maintenance technology programs. The private sector salaries they offered were substantial, far more than she could earn in military service. But Sarah had already made her decision about the next phase of her career. She would be leaving active duty the following year to pursue a doctoral degree in aerospace engineering at MIT, where she would research the application of artificial intelligence to predictive maintenance systems. The technology was still experimental, but early results suggested that autonomous maintenance could dramatically reduce the manpower requirements for keeping aircraft operational. Imagine a system, Sarah explained to a group of aerospace engineering students during a guest lecture at MIT, where an aircraft lands after a mission and within minutes, automated systems have diagnosed any developing problems and initiated appropriate maintenance actions. Routine tasks like fluid changes, filter replacements, and minor adjustments could be performed by robotic systems guided by AI diagnostics. The implications of such technology extended far beyond military aviation. Commercial airlines were particularly interested in autonomous maintenance systems that could reduce the time aircraft spent on the ground between flights. In an industry where aircraft only generate revenue when they're flying, any reduction in maintenance time translated directly to improved profitability.
But Sarah was also aware of the human implications of increasingly automated maintenance systems. Technology should enhance human capabilities, not replace human judgment, she emphasized during her lectures. The most sophisticated AI system is still just a tool. The key is ensuring that human technicians remain involved in critical decision-making processes. Her approach to autonomous maintenance reflected lessons learned from her F-22 breakthrough, the importance of human intuition and creative problem-solving in diagnosing complex technical problems. While AI systems could process vast amounts of data and identify patterns that humans might miss, they couldn't replicate the kind of intuitive leaps that had led Sarah to investigate engine mount degradation when everyone else was focused on other potential causes. The future of aircraft maintenance, Sarah wrote in a paper published in the Journal of Aerospace Engineering, will combine the analytical power of artificial intelligence with the creative insights of experienced human technicians. The most effective maintenance organizations will be those that successfully integrate these complementary capabilities. Sarah's transition from active duty to civilian life wasn't without challenges. After spending 8 years in the structured environment of military service, adjusting to the more flexible academic world required significant adaptation. But she found that her military experience provided valuable perspective on the practical applications of the research she was conducting. Military service taught me to focus on solutions that actually work in real-world conditions, Sarah explained to her doctoral advisor. Academic research sometimes gets so focused on theoretical elegance that it loses sight of practical constraints. Her military background also gave her credibility with industry partners who were funding her research. When Sarah presented findings about autonomous maintenance systems, aerospace companies knew that her recommendations were based on extensive hands-on experience with real aircraft and real operational challenges. As Sarah settled into her new role as a graduate student and researcher, she reflected on the unexpected path that had brought her from a small town in Ohio to the cutting edge of aerospace technology development. The journey had been challenging, but it had also been deeply rewarding in ways she couldn't have anticipated when she first decided to join the Air Force. The young woman who had been told that women don't fix jets had not only proven that assumption wrong, but had fundamentally changed how the entire aerospace industry approached aircraft maintenance. Her innovations were being used by air forces around the world, and her research was laying the groundwork for the next generation of maintenance technologies. But perhaps most importantly, Sarah had become a role model for other women considering careers in aerospace and technical fields. Her success had demonstrated that excellence and innovation could overcome any preconceived notions about who belonged in traditionally male-dominated industries.
3 years into her doctoral program at MIT, Dr. Sarah Chen, she had completed her degree ahead of schedule, stood before an audience of aerospace industry leaders at the International Conference on Advanced Aircraft Maintenance. Her presentation would introduce technology that would once again revolutionize how the world thought about keeping aircraft operational. Ladies and gentlemen, Sarah began, today I want to share with you the results of research that began with a simple question. What if aircraft could not only diagnose their own problems, but also fix them? The technology she was about to unveil represented the culmination of everything she had learned since that first breakthrough with the F-22 engine mount. Her research team at MIT, working in partnership with the Air Force Research Laboratory and several major aerospace companies, had developed the first truly autonomous aircraft maintenance system. What you're seeing here, Sarah explained, gesturing to a video display showing a sleek, robotic system working on an aircraft engine, is an AI-directed maintenance robot performing a complex engine inspection and repair procedure with no human intervention. The demonstration showed the robotic system using advanced sensors to scan engine components, identify microscopic stress patterns using ultrasonic technology based on Sarah's original diagnostic methods, and then use precision tools to perform preventative maintenance that would prevent future failures. The system incorporates machine learning algorithms trained on decades of maintenance data, combined with real-time diagnostic capabilities that can detect problems at the molecular level. Sarah continued,
But perhaps most importantly, it incorporates decision-making protocols that can adapt to unexpected situations, the kind of creative problem-solving that has always been the domain of human technicians. The audience, which included CEOs of major aerospace companies, military leaders, and prominent researchers, listened with rapt attention as Sarah explained how her autonomous maintenance system represented the next evolution in aircraft care. The robot doesn't just follow predetermined procedures. It can analyze unique situations, develop custom solutions, and even learn from experience to improve its performance over time. But Sarah was careful to emphasize that autonomous maintenance wasn't intended to replace human technicians entirely. The goal is to free human experts from routine tasks so they can focus on the most complex and challenging problems. The system works best when it's part of a human-machine team that combines the efficiency of automation with the insight of experienced professionals. The commercial implications of the technology were staggering. Airlines could potentially reduce maintenance costs by up to 40% while improving aircraft availability rates. Military forces could maintain higher readiness levels with fewer personnel. Even general aviation could benefit from automated systems that made aircraft ownership more affordable and accessible. Following her presentation, Sarah was approached by Dr. Lisa Martinez, the Chief Technology Officer of Boeing. Dr. Chen, we'd like to discuss a partnership opportunity with your research team. Boeing has prepared to invest significantly in developing commercial applications of your autonomous maintenance technology. Similar offers came from other major aerospace companies. Airbus wanted to license the technology for their next-generation commercial aircraft. Lockheed Martin was interested in military applications. Even companies outside the aerospace industry, automotive manufacturers, shipping companies, and energy providers saw potential applications for autonomous maintenance systems. But Sarah had learned from her military experience that the most important consideration wasn't financial return, but impact. I want to work with partners who are committed to using this technology to improve safety and accessibility, she told potential collaborators. The goal isn't just to make maintenance more efficient, it's to make advanced transportation more reliable and available to everyone. The partnership she ultimately chose reflected those values, working with a consortium that included MIT, the Air Force Research Laboratory, and 3 major aerospace companies. Sarah would lead the development of autonomous maintenance systems designed to benefit both military and civilian aviation. Her role as technical director of the consortium represented the culmination of a journey that had begun more than a decade earlier when she first walked into that hangar at Langley Air Force Base. The young airman, who had been skeptical about whether women belonged in aircraft maintenance, had become one of the most influential figures in aerospace technology development. When I first joined the Air Force, Sarah reflected during an interview with National Public Radio, I just wanted to work on airplanes. I never imagined that I would end up developing technologies that could change the entire industry. But the path from aircraft mechanic to technology leader hadn't always been smooth. Sarah had faced skepticism, discrimination, and moments of self-doubt. There had been times when she questioned whether she really belonged in a field dominated by men with decades more experience. The key, she explained to a group of young women studying engineering at MIT, is to focus on the work, not on the obstacles. When you're solving important problems and creating value, people stop focusing on who you are and start focusing on what you can do. Sarah's story had become an inspiration to women in technical fields around the world. She regularly received messages from young women who had chosen careers in aerospace engineering, aircraft maintenance, or related fields because they had heard about her achievements. I get emails from teenagers who tell me they want to be aircraft mechanics because they heard about the woman who fixed the unfixable F-22. That might be the most important impact of everything we've accomplished, Sarah told her research team during one of their weekly meetings. As Sarah looked toward the future, she saw endless possibilities for continued innovation in aerospace technology. Autonomous maintenance was just the beginning. Her research team was already working on self-healing materials that could repair minor damage automatically and diagnostic systems that could predict component failures months before they occurred. We're moving toward a future where aircraft are truly intelligent partners in their own care and operation, Sarah explained to a gathering of aerospace students. Planes that can not only tell us what's wrong, but fix it themselves and learn from the experience to prevent similar problems in the future. The small-town girl who had dreamed of working on airplanes had not only achieved that goal, but had redefined what it meant to maintain and care for the most advanced aircraft in the world. Her innovations would influence aerospace technology for generations to come. But perhaps more importantly, Sarah had proven that excellence and innovation could emerge from the most unexpected places, and that the determination to solve complex problems could overcome any preconceived notions about who belonged in the world of advanced technology.
10 years had passed since that cold morning when Senior Airman Sarah Chen first walked into the hangar at Langley Air Force Base to face an unfixable F-22 Raptor. Now, Dr. Sarah Chen stood as the CEO of Autonomous Aerospace Systems, a company she had founded to commercialize the maintenance technologies she had developed during her years in research. The company's headquarters, located in a gleaming technology park outside Boston, employed over 300 engineers, technicians, and support staff. Their autonomous maintenance systems were now operational at airports and military bases around the world, keeping thousands of aircraft flying safely and efficiently. When I look back at that moment 10 years ago, Sarah reflected during a keynote address at the Women in Aviation International Conference, I realized that I wasn't just fixing an airplane. I was proving to myself and everyone else that innovation can come from anywhere, from anyone who's willing to listen carefully and think creatively. The F-22 that had launched her career, Sarah's bird, was still flying, now with over 3,000 flight hours and a perfect maintenance record. The aircraft had become something of a legend in Air Force circles, not just for its operational excellence, but for what it represented about the power of individual innovation to create lasting change. Sarah's autonomous maintenance systems had evolved far beyond their original applications. Commercial airlines now used her technology to reduce maintenance costs while improving safety. NASA employed autonomous systems based on her designs to maintain spacecraft and launch vehicles. Even the emerging electric aviation industry relied on her diagnostic protocols to ensure the reliability of new aircraft technologies. The principles that guided my original diagnosis of the F-22 problem remain relevant today, Sarah explained to a group of aerospace engineering students during a guest lecture at her alma mater. Listen to what the data is telling you, even when it contradicts conventional wisdom. Look for patterns that others might miss, and never accept that a problem is unsolvable just because previous attempts have failed. But Sarah's influence extended far beyond the technical realm. She had become one of the most prominent advocates for increasing diversity in aerospace and engineering fields. Her foundation, the Chen Institute for Technical Innovation, provided scholarships and mentorship programs for underrepresented students pursuing careers in aerospace and engineering. Diversity isn't just the right thing to do morally, Sarah explained during a panel discussion at the National Academy of Engineering. It's essential for innovation. The most complex technical challenges require diverse perspectives and creative approaches that come from people with different backgrounds and experiences. The statistics supported her argument. In the decades since Sarah's breakthrough with the F-22, the percentage of women in aircraft maintenance roles had increased by 35%.
More importantly, the innovation rate in aerospace maintenance had accelerated dramatically, with new diagnostic technologies and maintenance approaches being developed at an unprecedented pace. Sarah's story had become a case study taught in business schools and engineering programs around the world. Harvard Business School featured her career in their curriculum on technical innovation and leadership. MIT's aerospace engineering program used her diagnostic methodology as a foundational example of how to approach complex problem solving. The Chen method, as it had come to be known in academic circles, wasn't just a technical approach. It was a mindset that emphasized careful observation, creative thinking, and the courage to challenge established assumptions when evidence suggested alternative approaches. But perhaps the most significant measure of Sarah's impact was the generation of young women who had followed in her footsteps. The aerospace industry now included hundreds of female technicians, engineers, and researchers who cited Sarah's example as the inspiration for their career choices. I get letters every week from young women who tell me they decided to study engineering because they heard about the woman who fixed the unfixable F-22. That's more rewarding than any technical achievement or business success, Sarah shared during an interview with 60 Minutes. One of those young women was Lieutenant Maria Gonzalez, a recent Air Force Academy graduate who had been assigned to Sarah's old squadron at Langley Air Force Base. Gonzalez had specifically requested assignment to aircraft maintenance, inspired by Sarah's story, and determined to continue pushing the boundaries of what was possible in aerospace technology. Technical Sergeant Chen, Dr. Chen now, showed all of us that innovation doesn't depend on your background or what other people think you're capable of. Lieutenant Gonzalez explained during a ceremony honoring Sarah's contributions to Air Force maintenance operations. The ceremony took place in the same hangar where Sarah had first encountered the problematic F-22 a decade earlier. The aircraft itself was present for the event, having been specially flown in for the occasion. As Sarah walked around the Raptor one final time, she was struck by how much had changed, not just in her own life, but in the broader aerospace community. When I first saw this airplane, she told the assembled crowd of airmen, officers, and aerospace industry representatives, I saw a puzzle that needed solving. I never imagined that solving that puzzle would lead to everything that followed. Colonel Matthews, now a general and commander of the Air Force Materiel Command, presented Sarah with a special recognition award acknowledging her, quote, transformational impact on military aircraft maintenance and aerospace technology development, unquote. Dr. Chen's innovations have saved the Air Force hundreds of millions of dollars and improved the safety and readiness of our entire fleet, General Matthews announced. But more importantly, she has inspired a new generation of technical innovators who will continue pushing the boundaries of what is possible in aerospace technology. As the ceremony concluded, Sarah found herself once again standing beside the F-22 that had changed her life. The aircraft looked exactly as it had 10 years ago, sleek, powerful, and intimidating. But now Sarah saw it differently. Instead of an impossible problem, she saw proof that any challenge could be overcome with the right combination of knowledge, persistence, and creative thinking. You know, she said to Master Sergeant Rodriguez, who had flown in from his current assignment to attend the ceremony, I sometimes wonder what would have happened if I had listened to everyone who said this aircraft couldn't be fixed. Rodriguez smiled, remembering the young airman who had insisted on investigating a problem that had stumped some of the Air Force's most experienced technicians. I don't think you were ever going to give up, he replied. That's what made you different. You saw a challenge where everyone else saw an impossibility. As Sarah prepared to leave Langley for the final time, she reflected on the unexpected journey that had brought her from small-town dreams to international recognition as a leader in aerospace innovation.
The path had been challenging, filled with moments of doubt and obstacles that seemed insurmountable at the time. But she had also learned that the most significant barriers were often the ones that existed only in people's minds. Assumptions about what was possible, who belonged in certain fields, and what constituted acceptable solutions to complex problems. The most important lesson, Sarah concluded in her final remarks to the assembled crowd, was that innovation doesn't come from following the established path. It comes from being willing to look at familiar problems from new perspectives and having the courage to pursue solutions that others might dismiss as impossible. The young women and men in the audience listened intently to her words. Among them were the people who would design and maintain the next generation of aircraft, who would solve problems that hadn't been imagined yet, and who would continue pushing the boundaries of what was considered possible in aerospace technology. The F-22 climbed into the clear Virginia sky, its engines synchronized in perfect harmony, a lasting testament to what could be achieved when expertise, creativity, and determination combined to overcome any challenge, no matter how impossible it might seem. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.